Hello, my name is McLaughlin, and today I'm going to be talking about some considerations for selecting a time course data analysis approach for pupillometry. And in particular, I'm going to be doing a comparison of growth curve and generalized additive mixed models. So I want to dive in and set up the context for what I'm talking about when I say time course data analysis. So there are a variety of methods used to analyze pupil data, and that's really the point of this conference, is to discuss these methods. I would start by breaking these into two categories. So the first of those two categories being summary measures. So this is when you have pupil response across a trial, for example, when you are taking that longitudinal data and you're summarizing it down to a single value per trial per subject. So you can do this by summarizing it down to the peak amplitude, so the largest value within your trial. You can also summarize it down to the latency, so how long it takes to get to that peak. And another option would be to identify an area within your trial in which you're going to take the mean value of the pupil size. And for all of these, what you're doing is you're taking this sort of rich longitudinal data and you're bringing it down to a single value, which is really useful. And it's widely used because then you can run ANOVAs very easily with the data and so on and so forth. For the present talk, I'm going to be focusing on a couple of time course measures. So this means that rather than summarizing down this data, we are treating it as actual repeated measures data, which is what the, recording the pupil size over the time is. It's a longitudinal measure. So there are a couple there are many ways you can look at longitudinal data, but because pupil data is nonlinear, I'm going to be focusing on a couple of the nonlinear approaches that have grown in popularity for looking at pupil data. The first of these is growth curve analysis, which is abbreviated as GCA, and the second is generalized additive mixed models, which is abbreviated as GAMMs. There are many more ways you can analyze time course data, and I'm sure some of them will be talked about at this very conference. And so just keep that in mind. I'm going to be focusing on these two because they're the ones that I have experience with, but they are not by any stretch your only options. My goal with this talk is to essentially hopefully give a whirlwind overview of each of these and discuss the pros and cons of each, so that if you are at a point where you have decided you want to use a longitudinal approach and you are asking yourself, which should I use and where should I start, then hopefully some of this information can help you make that decision. Essentially, I'm sort of thinking of this as, if I could give advice to Drew 3 years ago, what would I tell her? And so I'll go through some of the pros and cons I've encountered that relate to thinking about the type and shape of your pupil data, as well as the R packages available for each of these approaches. And I'll do a little discussion at the end of this talk that focuses on what's called temporal autocorrelation, which will actually be relevant for people who are already using one of these methods as well, because it's just an important thing to take into account in our models. So without further ado, I'm going to dive into a bit of a whirlwind overview of growth curve analysis. I want to start out by recommending a book by Dan Merman, which will be, of course, much farther in depth than what I can go into. It is the book that I use to learn how to use this method. And it's really excellent. It's actually fairly brief, and it uses R and a lot of examples in R. So I found it very, very useful. Also, when sort of setting the stage for what GCA is, I think the most useful thing is to start by pointing out that while growth curve analysis sounds like its own entity and something entirely novel, it's actually building on the framework of hierarchical linear mixed effects modeling. And I put linear in parentheses there because what we do by building on top of this approach is we make our models nonlinear. So if you're already familiar with the LME4 package in R, so LMER or GLMER, both of them work with GCA. That is the exact same framework we're building on. And if you're familiar with mixed effects regression from perhaps a stats course or your own, personal training, then again, this is going to be a very familiar foundation for learning this approach. And of course, because it's mixed effects modeling, we're going to be fitting random intercepts and slopes in addition to, our fixed effects of interest. At this point, you may be wondering if what I'm talking about is polynomial regression. GCA is different than polynomial regression, but a lot of the concepts are very, very similar. So I'll actually discuss, I'll discuss GCA building on some of those same concepts as well. The time to use in which you would want to use GCA is when change over time is not linear, which is going to be the case with your pupil data. This is also why generalized additive mixed models, which I'll get to after GCA, are most useful for pupil data, is because it's also a nonlinear approach. In classic polynomial regression, the way we take a linear model and make it nonlinear is by introducing higher order polynomials. So by this I mean we introduce time into our model, and we introduce time squared and time cubed and so on, depending on the shape of our data. In GCA, it's very, very similar, except the way we introduce those higher order polynomials is a bit different. So we'll be introducing what are called orthogonalized polynomials, and what orthogonalized means is statistically independent. So essentially the polynomials we introduce are not straightforwardly time squared and so on, and we do this because it helps remove collinearity issues from our model. And we incorporate our polynomials into these hierarchical models as fixed effects, and also it's recommended that you include them as random effects whenever possible. I'm going to go through an example with some data from our lab. It's not too important what this pupil data is, like what the experiment is. I don't actually have a legend here, but the big takeaway is I have some data, it's between groups, and I want to see if this blue group differs from this pink group. And so in this plot, we're looking at the change in pupil size on the y-axis over a period of time. And we can imagine for now that this is just, an entire trial here. What we do before we start implementing a growth curve model is we actually take that data from our experiment and we use a function in R called poly, which creates the orthogonalized polynomials I was just discussing. And it creates them along the same time window. And so this is basically something you're adding to your data frame in R. So here I've plotted essentially the three factors the three fixed effects that I've created for my model. So poly 1, that is your first order polynomial. This is a linear line. Poly 2 is a quadratic, and poly 3 is your cubic. And for this example, I've only made 3 polynomials, but you aren't limited. You can create much more complex polynomial shapes using GCA. In this case, for this example, I just chose this based on a visual inspection that indicated this was fairly cubic in shape. If at this point you're wondering how these shapes are going to help fit to this data, I have a short visual example that I can show you that hopefully will help conceptualize it. So the important key concept here is that when you add together lines, so for example, this linear line and this quadratic line, you can get a line such as the following. And there's actually a really nice walkthrough that Matt Wynn made that's available on his website that I would recommend if this conceptually is a little bit difficult to wrap your head around. But this is what we're doing with a growth curve model. We are introducing as factors in our model these sorts of shapes, and by doing so we can basically add them together and we can change our linear model so that it will actually fit to our pupil data. So this is what that ends up looking like. So this is the same data now. I have the data in gray in the background, and I have overlaid on top of it the model fits from a growth curve model. And so you can see that, and I'll show you the code from this in just a moment. But you can see that by incorporating these 3 polynomials into a typical mixed effects model, we have made it so that rather than a model fit that is going to be linear, we are now fitting to the shape of our data, which is, naturally curved. I want to walk through what this looks like in R, and I apologize to anyone who doesn't use R because I realize this is very R lingo heavy, this talk, but I thought this would be useful for anyone who's familiar with this function or R generally to sort of get an idea of how we are actually implementing GCA with the syntax. So using LMER, we first specify the y hat of our model. So what we're predicting here is the size of the pupil. I've specified that I want an intercept, and then I list the fixed effects that I want to include in my model. So the key thing to note here is that I have an effect of group. So that is my, pink versus blue line that I've been showing you. But right next to it, I have just put in the same place in the syntax, I've specified poly 1, poly 2, and poly 3. So they are functioning as fixed effects in the exact same way that my group variable is, in the same way that my fixed effect of interest is. The second line of this code in parentheses is specifying the random effects that I want. So here I'm saying that I want random intercepts for subjects, and also because I've nested each of those polynomials within subject, that means for every subject I can model the unique shape of their own pupil curves. And then of course the last thing that you have to specify is where your data is coming from in R. So using this function, I was able to fit a simple model to this data that I've been showing you. And the big takeaway here is not just that we want to fit a model to the shape of our data, but we're going to be looking at that model output. And so in this case, we can use log likelihood model comparisons and so on. And this will help us determine whether there is an effective group. It'll allow us to compare whether this blue group is different than this pink group. Whereas we could have done this with a summary measure, summarizing this down to a peak. Now we are incorporating all of this data in order to examine this effect of interest. So that is my whirlwind overview of GCA, and now I want to talk pros and cons. So first of all, I think one of the biggest pros of GCA, which will be the case for all but not a lot, but not all users, is that it should be a fairly easy transition for people who are familiar with the LME4 package. So if you're familiar with using mixed effects and R, then I think this is probably the easiest addition to your prior knowledge that you're going to make in order to look at time series analyses for pupil data. Another thing that might seem a little bit out of the blue, but is worth noting, is that there's relatively low computational demand for these basic growth curve models. It does take a long time to converge these models, but that's actually just going to be the case for any of these longitudinal approaches that you're going to use. All right, I'm going to talk about some cons now. So the first one I want to discuss is something that GCA is not very good at, and that is fitting asymptotic or similarly non-polynomial curves. So the simple explanation here is that polynomial functions can't fit plateau-like sections. So the data I've been showing you as an example is actually a really great example visually to look at this. At the beginning of this example data, I have a very flat section where there's no change in the pupil size. And when I fit my polynomial curves to this, where we see a fairly good fit on the right side here, but on the left side of my model, it is not fitting very well to the actual data. And this is something where you can, determine as a researcher whether it's theoretically important for it to fit here. So for example, for the pupil response, there's a delay in the pupil response. So maybe we don't care about that, but this is important in general when you're thinking about the kind of data you're going to be fitting with GCA, because GCA may not be well suited to the shape of your data. GCA has a really hard time with eye tracking data, for example, because we tend to get a lot of plateaus in the shape of that response. One of the other solutions to this that is very common is researchers will identify an area of interest that they're going to be analyzing. So here in this example, we can say this is maybe the length of an entire trial, but maybe I don't want to analyze the whole trial. If I know that the pupil response is delayed by 200 to 300 milliseconds, maybe I instead analyze from about here to the end. And that's an option you have, and then this curve will be able to fit better to your data, presumably. This, although, can give rise to another issue. So this is what I would call the area of interest issue. So I have an example here from a preprint by Jonathan Peel and Kristen Van Engen. This is a paper under review. It's actually looking at eye tracking data, but conceptually it's really useful because they were looking at how the area of interest that a researcher chooses to analyze can affect the outcomes of a growth curve model. So what we're looking at in this graph, this gray box is showing you the analysis window. So you can imagine fitting curves for however long this box is going. And these bottom two boxes here are showing you how the parameter estimates change and how the p-values change. And the big takeaway is that the outcomes of your model can be sort of drastically changed depending on what window of analysis you choose. And of course, this just gives rise to a whole bunch of researcher degrees of freedom. This is an issue. It's not an unavoidable issue. If you're pre-registering your data analysis approach, then you can specify, I'm going to start my analysis window here and end it here. Especially if you have some pilot data, you'll have an idea of what the pupil response in your data is going to look like. So this is something that can be worked around, but it is an issue that is worth keeping in mind. Okay, I am going to switch gears and talk about generalized additive mixed models now. I want to start out by listing quite a few resources this time. So I have been working with GAMMs for just about the last year, so they're a bit newer to me than growth curve modeling is. And these are the tools that I have found the most useful. So the first is an article that's fairly brief and really, really useful for implementing GAMMs in R for pupil data. The second is a book by Simon Wood, which is a lot denser. So I don't know if I would start with that as your resource, maybe ease yourself into it. And then the third is something I found more recently. It's a free webinar on YouTube by Gavin Simpson, and it's a really nice overview of an introduction into how to use GAMMs as well. Okay, so now what are GAMMs? So this is another nonlinear mixed effects regression analysis approach. The key concepts underlying GAMMs are what are called smooth functions. I'm going to show you a visual example of this in a moment, but I'm going to go through the basics verbally first. So to make a smooth function, the generalized additive modeling uses multiple base functions. You can think of these like building blocks that are going to sum up to make one long wiggly line that fits to your nonlinear data. This line, this smooth function, is obtained with maximum likelihood estimation, and there is penalization that is incorporated in order to avoid both overgeneralization and overfitting to the data. So I'm going to show you this visual example now. The idea behind this smooth function that we're fitting is that essentially what's going on in the background when you make a generalized additive model is there are a ton of what are called base functions being specified. So these are the colored functions underneath the black line in this function. So what I want you to imagine is that there is pupil data that follows this general shape of the black line. And so what you do is in R, you specify your generalized additive model and you feed your data into it. And what it's going to be doing is based on the specifications you've set, it's finding a bunch of these base functions that when they are summed together, added together, they create this black smooth function, which is a very complex shape. And it isn't necessarily strictly a polynomial shape. You can see that there's a bit of a flat line at the end here. And so what this means is that this approach is extremely flexible. It can fit so many shapes of data. It's really, really incredible, actually. But this is conceptually what's going on in the background. And I'm going to be sticking to a fairly simple example, but it's worth keeping in mind that there are almost an overwhelming number of ways that you can specify your model in R when you're using GAMMs. This is what it looks like in R. Again, this is a very simplified model. This is not necessarily the model I would use for an actual research project. This is just a very simplified overview. Again, we're using a function called BAM this time, but the syntax is pretty similar to LMER. We are specifying that we're predicting the size of the pupil, and then we are saying that we're predicting it with a fixed effect of group. So group, again, I'm using that same data here. So it's just that blue versus that pink line here. The next thing we specify is our smooth. So as I was saying, this is the key concept underlying this. We're telling this function that we want to make a smooth that continues over time, our variable time, and it's by group, our fixed effect. The third line here is indicating basically the random effects of this particular model. You actually have multiple options for GAMMs. In this case, I'm specifying a random smooth. So this means that for every subject I'm getting, they're each getting their own random smooth line. You could also do intercepts and slopes like you typically do with mixed effects regression. So this is sort of a broad overview of what it looks like to implement a GAMM in R. If we go back to that data, this is the same data as before. You may notice that there's more of the data this time. The last time I showed it to you for the growth curve analysis, I had chopped it off about here. But I'm including all of the data just to give you an idea of how GAMMs can fit to this full shape, which is, quite frankly, not a normal polynomial shape. So this is what the model fits look like from a simple GAMM model that I have created. And you can contrast this now with the growth curve analysis that I had done before. And so the big takeaways from this, whirlwind overview is that I was able to fit this flatter section a bit better using the generalized additive modeling. And I was also able to fit the entire trial of my data. So I sort of skipped over this when I was doing the explanation for growth curves, but I had specifically selected an area of interest from the get-go when I was showing you that example. I had decided to chop off my data here so that I would have a fairly cubic shape in order to be fitting. Whereas for generalized additive mixed models, if I was to analyze this for a research project, I wouldn't cut off my data. I would leave the entire trial length in this data. So it may be clear just from the explanation I was giving, but I'm going to go through the pros and cons for GAMMs now. Big takeaway from GAMMs, they are really excellent for fitting many shapes of data. So in particular, if you are going to be analyzing very long pupil trials, so for example, if you're going to be looking at some sort of task that has multiple evoked responses, so you're going to get a lot of ups and downs in your pupil data, then GAMMs are probably going to be what you want to use, because if you're going to get plateaus in between those evoked responses or who knows what, GAMMs will be able to handle all of those shapes. Another thing that is a huge pro of GAMMs that I don't really have time to dive into too much is the main package for implementing a GAMM model is MGCV, but there is a companion package called It's a Doug, and it is phenomenal. It's really important when you're doing these models and any mixed effects modeling that you're running diagnostics, model diagnostics, and making sure you're not breaking any assumptions. And the It's a Doug's package makes running those diagnostics exceptionally easy, and it helps you visualize everything that's going on in the background of your model as well. So that's another thing that I think is a huge pro of GAMMs. They are more complex, but the tools that have been created to implement them are all up to date and very, very useful. So a couple of things that GAMMs are not so good at. There is pretty hefty computational demand. Although I'll come back to this in just a moment and why it's sort of a moot point when you're comparing GAMMs and GCA if you're actually specifying everything in the model that you should be. The other thing that I do think is worth noting is that the learning curve may be steeper for some researchers. That was definitely the case for me, I will say. When I learned to use growth curve analysis, I was already on pretty good footing, because I was already familiar with mixed effects. And learning to use generalized additive mixed models, because the foundation of them is a spline-based approach, it's just a whole different world that I was unfamiliar with. And so the learning curve has been steeper for me, and that might be the case for other researchers. And so considering how much time it's going to take to learn this new method is something that I think is worth noting. Okay, one more thing I want to talk about. I want to take some time to discuss temporal autocorrelation. So there is an assumption of regression, these mixed effects models, that the residuals are independent. This is something that tends to be untrue in longitudinal data and these longitudinal time course analyses. This isn't specific to pupillometry or either of the two methods I was talking about. This is just a general issue that crops up for all of these different longitudinal approaches. So I have a visual example here. So on the left here, I have the generalized additive model that I fit to this data. And I apologize because I have the two lines here, but really what I'm plotting on the right is just the model fit not based on these two groups. the big takeaway here is what I'm plotting is over time, I am plotting the residuals. So this is the deviance of the actual data from the model fit. And you'll notice that when I plot this over time, we see this oscillation. What we would see if the residuals were independent, which is our assumption, that's the assumption in the, that we take for granted, that is an assumption we make for regression models. If this were random, then we would see a cloud, essentially. It would be distributed across time because of how I'm plotting it, but we would just see points going up and down randomly. And in this case, what we were seeing is super duper not independent, essentially. So this is a really easy visual diagnostic test. And what it's telling us is that we have autocorrelation of our residuals. And that just means that each of these points along the way is going to be correlated with the one closest to it. And this is an issue. And the reason this is an issue is because it can increase your chance of type 1 error, which clearly we do not want. There is a solution to this issue. So we can add what's called an autoregressive 1, AR1 is how that's abbreviated. And this is essentially something you specify in your model. And you don't have to do anything really, but you're just specifying in R when you're building your model that you want to include an AR1, and it's going to help account for and correct some of that autocorrelation. This is really exceptionally easy to do in GAMMs, and there are, again, the diagnostics in the It's a Doug package make it even easier to visualize the before and after when you're introducing this AR1 and correcting for that autocorrelation. It's a little less straightforward with GCA, and so this sort of packs on to the other cons of GCA I was discussing. And the reason it's less straightforward is because AR1 specification is not available in the LME4 package. So it isn't the case that you can't specify an AR1 for a growth curve model. It's just that the most common package, LME4, doesn't have that option available. There is a way to do this, and this is something I've been playing around with in the last few months. There is a package called NLME, very similar to the LME4 package. I think it might even be by the same creators. It is also for fitting mixed effects models. The syntax is just a little bit different. And you can specify AR1 using that package. There is intensive computational demand and intensive processing time. It is very tedious to do this. And there are some other little annoyances that have cropped up for me. So that NLME package has some limitations that were probably very specific to the data I was fitting, but nonetheless, they sort of were all in line with that package being less updated because it's less popular than LME4. So big takeaway here is that you should correct for temporal autocorrelation. This is an important thing. You don't want to increase your chance of type 1 error. You can do it for both of these approaches I've discussed. It's going to be easier for GAMMs, and for GCA, you're going to have to basically find some workarounds. And in both cases, as soon as you introduce this AR1, the computational demand of these models is really intense. So it's something that I can't run on my little MacBook Air, which only has 8 gigs of RAM. And that's something that is a cost for both of these approaches. All right, so I'm going to summarize and wrap things up now. So back to those original questions and the aims of this talk for me, which are which of these models, which of these approaches should you use? Where should you start? My recommendations, if I were to give them to myself 3 years ago, would be that you need to know your data, maybe collect some pilot data if you're very unfamiliar with pupillometry. And you just need to determine basically for your research, do you expect pupil response with plateaus or a ton of evoked responses and many peaks across your data? Essentially, are you expecting some non-polynomial shapes that are going to be really hard to fit? Another way to think of this is if you're going to have a ton of evoked responses in your data, if you were to use growth curve analysis, would you have to essentially segment your data a bunch of times and do multiple analyses? Because if that's the case, then you should really be using GAMMs. And the other thing that I would say is consider your prior knowledge and where you want to invest your time. I mean, a part of me wishes I had invested the time learning how to use GAMMs from the get-go, but I also think that growth curve analysis is really well suited to the kind of experiments I'm running. I'm getting a single evoked response, and it's pretty easy to select a time window that will be able to fit to the model shape, and that's worked really well for me for the research studies that I've been conducting. So this is just something that is going to vary from person to person, but I think understanding how each of these approaches will work for different kinds of data and understanding essentially the tools available and things like that are really good starting places for making this kind of a decision. I want to give special thanks to Jonathan Peel and Kristen Van Engen, as well as their labs. You can find me on Twitter, and you can also email me. My email address is there on the screen. Thank you for your time.